So it cuts down the signal-to-noise ratio even if it is completely out of range. What we further learned, theoretical solutions and simulations are unlikely to work in real-life scenarios. I hope that those guys at universities, I'm sorry to insult you, should go away from their network simulators and start real-life tests. And the optimizations, well, I think first we should make it work, then we should make it stable, and later we should worry about routing the whole universe in one subnet. Proactive routing algorithms depend on synchronized information, and therefore, because we have lots of interference and collisions, transmissions must be redundant. So new message types introduce a new source of failure and new information that has to be synchronized, otherwise it will cause confusion, and so it causes new headaches. What we did after Wizard of Oz was we disabled hysteresis at first. We disabled the multipoint relay section in the configuration file, and we started working on implementing a route calculation depending on packet loss. I'll explain this further. And the last thing that is new in the CVS version and in the upcoming 0410 release is a link quality fisheye feature that will replace the multipoint relay attempt of INRIA. OLSR, like I said before, it minimizes hop count in routes, hence it favors longer and lossier links. So the default OLSR daemon will choose a route A, B, C, but between B and C there's 30% packet loss. There's an alternative route with very low packet loss, but most routing protocols like OLSR, they would not choose such a route. They will always blindly choose a route with the shortest path, and combined with the hysteresis, it will very soon drop the link to B and forget about it and start rethinking about the network topology. We did some research with other metric ideas. We tried to measure the latency of packet transmissions, but this is a really hard task. We didn't get good results with it. Another idea would be to measure the throughput of a link, but I have no idea how to measure throughput without issuing traffic, and that would, of course, generate a lot of overhead. Well, the protocol is working with broadcasts on the UDP traffic. So what we did was we implemented an ETX-like solution. ETX was a paper issued by somebody at MIT, which suggested that every node should send some UDP packages, and the other nodes, they expect to receive those UDP packages, and by the number of packages that are expected divided by computed the number of packages that are lost, we calculate a quality of the link, a likelihood that a package has to be retransmitted. We named it LQ. So here, A transmits data to B, and the likelihood that the packages come through is 90%, and the acknowledgements that come back from B have a likelihood of 70%. And we calculate the ETX value, which is just, I missed the English word for it, the reverse. Der Umkehrbruch. Okay, and this value here in the example with 1.59, it's just added as a metric when calculating the routing table. And the result we introduced the ATX in 0.48 of OLSR, and we had some bugs in the first implementation, but even with 0.48 and now with 0.49, many people successfully have built mesh networks all over the world. There are mesh networks here in Berlin. We have 180 nodes, I think, at the moment running. In Leipzig, they have 60. In Rostock, I heard about 100 nodes, and they are all operating in Rostock in ad hoc mode, all based on WRT54 from Linksys with OpenWRT software, and they're really satisfied with it. Still, we had some issues with 0.49 under high traffic load. As links saturate, we faced routing loops, and the new release 0.410 will address these issues. I learned that networks that are not saturating their Wi-Fi links are not affected by these routing loops issues. We have a killer feature in Berlin, download from dev0, which saturates the bandwidth, and are really funny effects that you can view when you watch it. We have 2 mesh clouds at the moment in Berlin that are independent. There's one in Hohenschönhausen and Weißensee, and one here in the center of the town. When some freaks interconnected both mesh networks, we finally saw that we now pushed OLSR to the limit. We always knew that there is an extent to what OLSR can work, and we wanted to find out when it actually crashes, when actually the weakest CPUs start glowing and cannot handle to recalculate the routing tables all the time. And with more than 200 nodes, we faced this problem. So the older versions of WRT54 with only 120 megahertz CPUs, they couldn't handle that CPU load anymore. They were not able to recalculate and started sending false messages and so on and so on. So the problem that we are addressing now with the new and upcoming release is the problem of routing loops. It's a basic problem which can always occur in a proactive routing protocol. Because every node maintains a routing table, there are problems if the routing tables are not in sync. Well, in such a big mesh like we have here now, the routing tables in fact are never in sync. Never, never, never. But usually this is not a problem. If you have a link with 10 hops, a node on one end of the mesh may have the illusion that it exactly knows the exact path the package would go when it is sending payload to a node 10 hops away. But this is very likely an illusion. But it doesn't harm the communication. A node somewhere in the mesh only needs to know which neighbors are the right choice to hand the packages over to get into the right direction. Nodes that are more far away from the node issuing the traffic and nearer to the node that is intended to receive the traffic, they know better about the routes because they have information that is more in a timely manner, that's more up to date. So here is an example of what we saw when we looked into OLSR daemon and what it was doing in the nodes. Everything is fine here except that D has a different idea about the best path to E. There was formerly a link existing between B and E, but B and E just learned that this link is not usable anymore. D still has a link, the others know about it. But D thinks the best path to to send packages to E is sending them to B. So the package that comes from A or is forwarded by A from somewhere goes to B, C, D, B, and then we have the loop. And the packages, they have a time to live, which is a good thing, because without a time to live stamp, some packages would run around in our network for ages until we cut the power. So it is looping very fast in a few milliseconds. It is looped several times, the time to live is exceeded, and the node that drops the packages sends a message back, hey, time to live exceeded, no route to host. The problem occurs all the time when the routing tables are not in sync. And my thesis is that it only occurs amongst a few neighborish nodes, a few adjacent nodes, because it's very unlikely that the packages is running in a routing loop that goes from Hohenschönhausen to Mitte and then back to Weißensee. That's very unlikely. So it's more likely it happens between only a few nodes. It can very well happen that B thinks, hey, the best way is to send it to C, and C thinks, hey, the best way is sending it to B. The nodes are not intelligent enough to just say, oops, I just had this packet. So what we learned about the routing loop issue is it occurs when topology information is not in sync. Loops happen among adjacent nodes. Interference causes topology information loss. Payload traffic causes interference and therefore topology information loss. So topology information must be redundant and sent often, more often than hello messages to provide information timely. Imagine if you send topology control messages every second and hello messages every 5 seconds, chances are you have sent that information that something changed 5 times before something changes again. That was not correct, forgive. And the technology of multi-point relays, which should reduce the protocol overhead, it doesn't help here and with these issues. The only thing that helps is send topology control information very frequently, very often. But of course, with multi-point relays, this is not possible because the mesh would just suffer from so much topology control messages that are issued from every node all the time. So we started reusing idea which we already used before, which was introduced in mobile mesh. It's called fisheye routing. We call it link quality fisheye. Those topology control messages, they have a time to live stamp. And we just, with a simple hack, we manipulate the time to live stamp. We send packages with a time to live of 1 very often. With a time to live 2 quite often. With a time to live of 3 often. And with a time to live of 255, which is now the default in the previous releases, every now and then. At the moment, every 13th package is a topology control message that is sent all over the whole mesh, flooding the whole mesh. The result is that the neighbors in the green circle, if we issue topology control messages every half second or second, they are updated every half second. At the moment, with the set that we have at the moment, these neighbors, they get it every 2.2 seconds. In the blue ring, they get it every 4 seconds. And in 255, they get it every 6.5 seconds. I'm not really sure about it. In the effect, so distant nodes have a hazy view about the topology in the network, which is sufficient. They don't have to know precisely about the structure. They only have to know, yes, out there are some nodes and this is their IP. They exist, and they have a